Started up kind of slow. How many sig figs in each of those measurements?
4.
Both have 4?
No, for the first one, 4.
Uh-oh, come on, reconnect. There it goes.
And then for the second one, all of them.
So the first one has 4. I only see 3 there. Why are you saying that 0 counts as a sig fig? Before and after. Why do we have to check both? What's our rule? There's no decimal point, so we have to look for that decimal point. And because there isn't, that 0 is significant. Okay, so we end up with 4 sig figs. The next one, every single one of those is a significant digit, right? Okay. What is the difference between how those were measured? That's an interesting question. What do I mean? How were those distances actually measured? Okay, with the top one measuring to 4, what was I measuring by? Meters? So I know that that is a 0?
No.
So was I measuring by single meters?
No.
What was I measuring by? Hundreds of thousands of meters. Okay? That's why the sig fig goes out there. Okay? In the second measurement, I was measuring by meters. And I know that because I see a significant digit at that location. Okay? So these two distances are ultimately looking at the same thing, the distance between Earth, is that what I said it was? Yeah. Assumed Earth to Moon. Okay? Are looking at the same thing, but carries slightly different meaning because we changed how we made the measurement. Okay? If we're looking at the distance between the Earth and the Moon, do I care about that last 1 meter? Probably not. Why not?
Because the number's so big, it's insignificant.
406 million to 1 meter. Right? The scale difference there is so drastically different that we can ignore it. Right? One may be more precise, but for the sake of what we're trying to do, which may just be how big is that distance, we don't need that exact measurement. Right? If you're going to drive across country, you're not going to nail it down to the specific inches in each of that distance. You're probably going to ballpark the miles, so a couple thousand miles. Right? Is that 100% precise? No, but it gets us to where we need to be. Okay? Or a rough approximation. It can give us an idea of how much time it's going to take us. Same thing is happening with our measurements. So we want to be careful when we go through and do our measurements to account for that and be aware of what we're thinking about when we make those measurements. Okay? The next part that becomes tricky, which is where we ended the last lecture on, was taking a look at that measurement and saying, actually, that doesn't have 4 sig figs, it has 6. That when I took that measurement, I did measure by thousands of meters. So that I know for a fact that that 0 is absolutely not 1 through 9. But the very next 0 I have no clue about. Okay? So as this is written, I don't have a way of distinguishing those two zeros. Because according to my sig fig rule, those zeros hold the same meaning. Okay? Well, to make it significant, I just say, well, then it's not actually 0, it's 1. Well, the problem with that is, what did we say? It's not 1 through 9. So how can I ensure that those two zeros become significant without making the last zeros significant? Right? By adding a 1, we change the meaning of the number. Right? So that doesn't quite work. Right? There's an option to add a decimal point. 406, 300, comma, 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 decimal point. But what does that now mean? Now all of those zeros are significant. The purple one I'm saying I know something about. I don't. So I can't just add a decimal point. Well, those other zeros weren't significant digits, so maybe I just placed the decimal point in the wrong spot. Right? Does that change the meaning of my measurement now? Yeah, I went from 406 million to 406,000. You won the lottery, millions, but we forgot that some of those zeros weren't significant. We didn't really measure them, so instead of giving you 406 million, we're just going to give you 406,000. That's still a pretty big number. We still might be okay with that. But there's a pretty big drop in value with that. Right? So how can we ensure that those zeros, okay, as placeholders are accounted for? Yes, we have to bring in the decimal point to show the meaning of those last two zeros, but we have to be careful with where we place it. Right? What we'll end up doing is shifting to scientific notation and calling this 4.06300. Notice the last zero I'm marking lines up. So now that zero is significant. But now I'm not going to include any of the purple zeros. Right? Well, isn't this an even bigger issue? I went from 406 million to now 4. Okay. Now you probably won't accept that lottery ticket. No, you false advertising. I'm going to sue you and win $5 billion. Okay. We have to include the placeholder information, and that's what our powers of 10 can do. Our powers of 10 tell us that that 4 does not belong in the ones position. It belongs in the 100 million position. Okay. So how far do I have to shift that decimal? Right, well, it went 1, 2, 3, 4, 5, 6, 7, 8 places. So I can call my power of 10 to the 8. Now the question is that number really big or really small? Really big, which means that 8 needs to be positive. Don't want to show the positive? That's fine, you don't have to. Okay. Now when we look at that measurement, how many sig figs are there? Well, the 4 is significant, the 6, the 3. Since I have a decimal point, all I need is a sig fig to the left. And we have 6 sig figs. And if we go back to the initial question, that's exactly what I wanted. So scientific notation can allow me to include zeros as significant digits, when in other cases they would be ambiguous. We don't really know. Okay? This is typically why they add extra rules into sig fig rules, is because of scientific notation. Scientific notation isn't the reason we need more rules. Scientific is the reason that simplifies everything else. Okay? That's the point of scientific notation. Kind of make sense? Okay. So now, our metric system. This is the system that we'll be doing most of our measurements in for most of the semester. However, within this first unit, we'll kind of mess with it a little bit. Okay, so to start off with, we've got length measuring in meters. That's going to be our core unit. Mass is grams, volume is liters, and time is seconds. These are all what I would call core units instead of basic units. And we'll look at why that becomes important later. Okay. It's not a big deal. It's just a way to kind of identify it. Okay, that is our core unit. So whenever I look at a measurement in length, I'm going to be concerned about the meter unit. Okay? Because those are the core units, that tends to be where I branch off from and do all sorts of other conversion systems, is from that core unit. Okay? What happens if we have really large measurements, like that 406 million meters? Right? Well, just saying it, we already introduced a way to fix that. I didn't say 406, 000, 000. I said million meters. I've already introduced a term that allows me to not include all those insignificant zeros. Okay? What we do within the metric system is we use powers of 10 to help simplify. That's where our millions are coming from. Okay? Or sort of millions are coming from. So if we go through and take a look, what we will do is modify the core unit. So what we have in the middle here is our modifiers. Those are all modifiers of the core unit. So if I want to look at million, that's this one, right? That's a million? Yeah. Million is mega. Okay, so if I wanted to say 406 million meters, okay, million is not a standard unit of measurement. So I would change that to now 406 megameters. That capital M now accounts for the power of 10, scaling that 406 up to the million section. That's its sole purpose. Okay? It is a power of 10 multiplier. The powers of 10 can be super important to go through and memorize because we have to be able to manipulate and use these. How often are we going to deal with teraliters? 10 to the 12th liters. Okay? When we go into the lab, what do we measure volume by? Milliliters. We're now talking 10 to the 12th liters versus milli, 10 to the minus 3. Okay? That's a pretty significant difference. Okay? That's so large, in fact, we're probably looking at the scale of the ocean. We're not measuring anything on that scale. Okay? So is it going to be useful to memorize tera? No. How about giga? Mega? Mega starts to get into a reasonable range, but again, those are still really, really big numbers. Kilo? Kilo shows up, right, and other things beyond the drug trade. Right? We probably won't even encounter kilo for that matter. Right? As a unit, it's one that you should memorize because we could look at, say, the mass of a human in kilograms. Okay, so that could become important. So we would go through and spend the time to memorize that. But in the lab, we aren't going to do that. Right? Our measurement of mass in the lab, we're looking at grams. When am I going to expect you to measure out 1,000 grams? Okay? A lot of the chemicals we work with can be hazardous. Okay? Typically what happens when we look at hazards is not the chemical, but the amount of the chemical. Okay? Cyanide is perfectly fine to work with as long as you don't work with a very large amount. Okay? Kilograms of pretty much anything will kill you. Okay? So we don't want to measure out in kilograms in the lab. In the lab, we'll probably be looking at grams or milligram amounts.
Why don't we, like, a lot of people use, like, hecta or necta. Like, I noticed a lot of people, like, these graphs, like, after kilo, I don't mention hecta or necta.
A lot of the times those units don't get mentioned. It depends on the scale of the system that you're looking at. So sometimes you'll hear reference to hectacre, right? Because you're looking at a large amount of land. Right? So depending on what scale you're working in, you might see different systems pop up. For the most part, the large ones are now so large that we can't manipulate. Right? Same deal with the small ones. Pico, 10 to the minus 12th. Okay? You're looking on the order of an atom. Okay? We can't just reach out of the air and grab an atom. That doesn't work. Okay? Which means we probably won't ever see pico. Okay? Nano, probably starting to move into the bond distance, so that gets a little bit larger. Okay? But that's still not very easy to deal with. Micro, medications, okay? A lot of drugs that we take that are beneficial. Oh, jeez, that was just snowballed out of the... pharmacy, let's do pharmacy, because that sounds nicer. Okay? Pharmacists might work with things on the scale of micrograms. Right? So that could become more useful, particularly if you want to become a pharmacist. If you don't want to become a pharmacist, that's a really small amount. So what can we move up to? Milli. Okay, now milli ends up being a more common unit. You all did that lab where you used the balances. What was the precision on the balance? Some people got that wrong. That's okay. Usually, or most people on Thursday got that wrong. That's my fault. I apologize. What was the precision on the balance? Milligram. Right? So that was the smallest unit of measurement that our balance can measure out. Right? So milli becomes really important for us to memorize. Okay, after that, I would argue centi becomes important for centimeters, okay, a unit of length. Deci is now in that decent kind of range. We've got kilo at the high end, and then we've got milli and centi. Deci's right in between. So theoretically, deci would be one we would use. It turns out that we don't use it all that often because we could simply either jump to centi or keep in the core unit. We're only shifting off by a single power of 10. Okay? So which is easier to write? So if I take a measurement, let's take an example here. I have 10 grams, or I have 1 decigram. Whoops, did that backwards. 0.1 grams, or I have 1 decigram. Which is easier to write? They're about the same, right? And as long as they're about the same, we'll go with whatever we stick with. If you try to say decigram, you'll find doesn't roll off the tongue like, say, milligram does or kilogram does. So why do we not memorize deci? Because it's just not fun to say. Okay? We say, well, that's silly. Yeah, most of science is silly. Okay? We come up with approximations to shortcut our lives through our systems so that we can get to answers quicker. Okay? Decigram doesn't really shortcut our lives, and it doesn't make our life more enjoyable because it sounds cooler to say. Okay? So there's no real need to go through and use it. Does that mean it doesn't show up? It's not true at all. It does show up. It just doesn't show up quite as frequently. Same deal with the tera, giga, mega, micro, nano, pico. All of those do show up, and I do expect you to run calculations with those in your homework. I don't expect you to memorize those because the value added by going through and memorizing that isn't useful. I do expect you to memorize the other ones. Okay? So those three are the super important ones. We can even see I've boxed it on the slides. You need to memorize those. What do I mean by memorize? Lowercase k means kilo. Okay, that's English. I don't care about English. Sorry. That's actually sorry to my English partner, by the way. Not to you guys. What do I want you to memorize? K is, the hint, it's not kilo. How about the other direction? Right? It's 1,000. I would argue you shouldn't memorize 1,000. Okay? You should memorize the power of 10. 10 to the third. Same deal for centi and milli. Okay? C for centi means 10 to the minus 2. Milli means 10 to the minus 3. If you hold those three pieces of information, that can simplify calculations later on. And you don't have to look them up. And so ultimately, when you are told to memorize something, the reason we're telling you to memorize it is not because we think it's important to memorize. It's because we realize that when we went through and did these classes, we used that information a lot. If you don't memorize it, what do you have to do? Look it up. We're trying to provide you a shortcut so that you don't have to look things up quite as frequently. That's it. And since everybody's looking at me kind of bored, then you can do this part. Convert that number into the new unit. Okay, and if you got questions, well, let's try that. Do you guys want me to do an example, or you think you got this? This is straightforward and easy. Example? Okay. Let's take a look at the first one. Okay, notice that what I'm telling you to do is not jump straight into the number in the new unit. I'm asking for scientific notation. So if we convert this first number into scientific notation, it would become 1 decimal point 2. Notice there's no decimal point there, so those zeros are not significant. Okay? Times my power of 10. Well, how far did I shift? 1, 2, 3. Was my starting number big or small? Big. A positive 3, and then I include my unit. Most people don't like seeing the positive, so let's get rid of that. The new number and unit is now going to become 1.2, but now I've got a power of 10. What did the power of 10, 10 to the third, mean? Kilo. And I have kilometer. Really? Yes. Do the others. So we're going to skip the second one for the moment. Somebody brought up an interesting question, probably unintentionally, but they brought it up anyway. So, third one. We write our scientific notation, 1.2. We shift the decimal 2 places. So it would be 1.2 times 10 to the second. Is that starting number large or small? Small, which means that needs to be negative 2. What is negative 2? 10 to the negative 2, sorry. Centi. So this becomes 1.2 centiliters. Can we do that? Yeah. Do we? Probably not. We probably stick with milliliters. Okay, but that's fair enough to do that. All right. How about the last one? It's still 1.2, and now we shifted 1, 2, 3 places. So that would be, let's deal with the powers of 10 first. I like where you're going. 10 to the negative 3, why do we say negative? The number was small. Right? 10 to the negative 3 is milli, and we get milligram. Right? Let's go through and make an adjustment up with that second one now. Or questions about what's up there? Okay. So first, let's actually go through and do this. 1.2, 10 to the minus 2, right? Right? Which would come in as centiseconds. Is that fair? Yeah, we're allowed to do that. Again, we typically don't, but we're allowed to make that measurement. Okay? How many of you like decimals? Okay, one person. Okay, so most people have problems with decimals. So what we might go through and do when we set up these conversions is saying, well, 0.012, that's confusing because that's decimals. Okay? Yes, I've converted this to scientific notation, but that's still decimals. Okay? How can I change that number to make sure it's not decimals? How many places would I have to shift the decimal point to make sure I don't have a decimal? So 1, 2, that would be 1.2. I don't like decimals, so I'll shift it one more. If I do that, what happens? Would I have a decimal value anymore? No, I'd have 12. And I'd have 12, how many times did I shift the decimal? 3 times. Was that number big or small? Small, so that's a negative 3. What does this come out to as a final answer then? 12 milliseconds. Right? There's no more decimal now, so now I look at it and go, I understand 12, because I have 10 fingers, that just means I need 2 toes added to this, and that works. And you might go, I'm not making fun of you, that's literally how we work. Okay? That is what the human brain does. That's not your brain, that's everybody's brain. We accept 12 milliseconds a heck of a lot better than we do 1.2 centiseconds. Okay? Because we can wrap our head around that 12 a lot better than we can 0.2. So depending on what we're trying to represent, we may shift the decimal point more or less to keep some meaning, allowing our pathetic human brains to deal with that. Yes?
Would it matter if you did centiseconds or milliseconds on the test?
Would it matter on a test? Well, let's rephrase that. If I asked for centiseconds, is it going to matter? Yeah. Why? I asked for centiseconds. Okay? So where it's going to matter is what was the unit that was asked for? What was the measurement? So you do have to read the question. Sometimes I may say, well, I think 12 is easier for me to understand, so I want to see it as units of 12. Okay? Sometimes I may decide let's just stick with centiseconds because I think it's fun to say centiseconds. Even though nobody on the test should be shouting out centiseconds. That could be a fun question. Okay? So we may have to adjust depending on what is asked of us. Okay? That's for the lecture. As far as the lab goes, how would we adjust? Well, what if the stopwatch we're using doesn't measure in seconds, it measures in milliseconds? Well, then what am I going to report everything to? Milliseconds. So it all depends either on the question asked or the device used. Make sense? Okay. So these fractional notations bring in conversion factors. Okay, so we can now potentially convert between those individual units. So for instance, 1 kilometer, 1 km, is equal to 1,000 meters. Okay? And we have the English, and then we have the mathematics behind that. Both of those are useful, and both of those you are required to translate to bring into a usable device. Right? So 1,000 meters and 1 kilometer. Notice I used the 1,000, and I said that was bad to do. So let's not call it 1,000 anymore. Let's call it what it is, 10 to the third. That's not an eraser. Let's try that. Right. Does everybody see the relationship between both of those statements, both the English and the mathematics? You say no, that's okay. If you say that's obvious, that's fine too. Do you see the relationships there? There are 10 to the third meters in 1 kilometer. That means 1 kilometer equals 10 to the third meters. Yeah? Okay. Why is that mathematical expression now more useful than the English? I can plug numbers in. What do you mean plug numbers in?
Like, if it's kind of like an equation?
Well, it is an equation. It's an equals.
Yeah.
Okay. The power of the equals is that I can shift things from one side of the equation to the other, and vice versa. Okay. So for those of you saying, well, now I can use a conversion. I can't really do a conversion yet, but I can use this to create a relationship. That relationship I can then use to do conversions. What do I mean? Okay, well, 1 kilometer is equal to 10 to the third meters. Right? How can I get the kilometer unit? The Wi-Fi is acting up today. How can I get the kilometer unit to the right-hand side of the equation? What would I have to do? Okay, we could try and subtract 1 kilometer. Okay, what are we subtracting that 1 kilometer from? Okay, can't answer that question. That becomes problematic. Okay, so what would be left? Okay, what would be left?
No.
So we'd have 0 equals to 10 to the third meters minus 1 kilometer. Right? Which should equal 0. That's valid. That's a valid expression. I want to now know how many kilometers are in 4,000 meters. How'd you do that? For those who are going, yeah, I thought it out. Yes, that's awesome. Your brain is fantastic at doing these simple conversions. And this is one of the things that we're going to fight through for this unit. Okay? Do not do this in your head. What did you mathematically write down to do that? Okay? Divided by kilometers. Does that look like it's going to work? What happens to the meters and kilometers as units? Do they cancel out? If I take x and then divide by y, does x and y cancel? No. Okay. Now I hear divide by meters. Okay, so you're just guessing. There are only two things, so guess, of course you'll eventually be right. So let's pause. We don't want to just guess and jam things in until Mike just says, oh, you did it right. No. Okay. The whole point of the English and the mathematics here was to give us a system to solve this expression. When you subtract it through, yes, you got kilometers on the other side. Great. Can you use that over here? No. Okay. Is there another way to get the kilometers over to the other side? The The answer to that question, in case you were wondering, is yes. Yes, there is. What does y equal? Two. What'd you do? Divide both sides by the same thing, and what happens? Those will cancel, and we'll get y equals 2. How did I get the x onto the other side of the expression? Did the same thing to both sides of the equation. Because if I do the same thing to both sides of the equation, it's the same as multiplying by 1 or dividing by 1. It doesn't change the meaning of the expression, but it does allow me to simplify and cancel things. Okay, so what do I mean? Well, over here, how can I get the kilometers over to the other side? I can divide. I'll divide both sides by 1 kilometer. Okay, and I would get 10 to the third meters over 1 kilometer equals what? Equals 1 kilometer. I have kilometers in the denominator and the numerator. What is 50 billion divided by 50 billion? Pineapples divided by pineapples. It's still 1. Anything divided by itself is 1. Right? So 1 kilometer divided by 1 kilometer is 1. Well, Mike, that was obvious. That was just like subtracting the same thing from the other one. Yeah, okay. Could I have done it a different way? Could I have gotten the meters over to the other side? Yeah. You're like, well, and again, Mike, I don't see the point. Why would you do this? Well, let's bear with me. Right? And I'd get 1 kilometer over 10 to the third meters equals 1. What is 1 times 6? 6. 1 times y. Y. Okay, so if I multiply anything by 1, it doesn't change the identity of the thing, right? Okay. 1 kilometer over 10 to the third meters is 1, right? So I'm going to multiply in my expression here 4,000 meters by 1. Everybody okay with that? Except what did I say 1 was equal to? What is 4,000 divided by 10 to the third? 4. What did you say the answer was? 4. Wait, using a mathematical expression and rearranging it so that it equals 1, I can then substitute 1 into virtually anything I want, and I can do a unit conversion? Yes. It's a beautiful system. And the reason why we don't like doing this is because we're like, all we do is divide by 1,000. It was easy. There was even a suggestion of divide by 4. Remember, there's only so many different things that you can convert at this point. Right? And eventually, you've already processed what it is in your head, but you don't have the intentionality behind that process to understand it. You're doing it right. You're doing it great. Because you understand the meaning of meters and kilometers and how to do a simple conversion. But what happens if I change meters to pineapples and kilometers to snow cones? What is the relationship between pineapples and snow cones?
Nothing.
Maybe it's nothing. Maybe there is a meaning behind it. What if I make it moles and grams? Is there a meaning behind those? Well, I don't know. Those are, grams make sense, but moles, why do I care about fuzzy little animals? Okay. We invent units to measure different things, and those units we have to be able to deal with and convert. If we don't have a process or the conceptual understanding of that thing to make that conversion, we're dead in the water. What we are looking at here is a process within this unit. Okay? And for those of you saying, God, you said process a lot. Okay? Feel free to count it out. Guarantee you will probably hear process more than 1,000 times for the rest of the semester. Okay? That is what you were working on trying to learn in this class. Not chemistry, but the process behind how we think and how we process knowledge. Okay? That's what we're working with. The English is how you will see every question. That's what happens in lab. That's what happens with the scientific method, because we start with an observation. An observation not in, well, I know that the force of the apple falling down must be pushed down by gravity, and that equals this and that and this. There's no equations when the apple falls. It's, ow, the apple hit me on the head. Why is it hitting me on the head? Okay? An observation in English, or German, or whatever other language, then a hypothesis in that other language. The experiment is then going through and trying to convert that into a numerical system, allowing us to convert and come up with relationships. Okay? So we have to be able to interpret at all levels of this. Okay? So every conversion, n equals, I can now rearrange that to solve for 1. 1 can now be substituted into virtually anything. Which one do I want to use? Okay. If I gave you another unit system, let's say I said that there is one, hey, why not? I know that's not how you, I think that is how you spell pineapple, equals 4 snow cones. Which equation do I want to solve for 1? Pineapples to snow cones or kilometers to meters if I want to solve the relationship between meters and kilometers? I want the kilometers and meters one. I don't care about snow cones and apples. Why? Because those aren't the units I'm working with. So you will have to choose what units to deal with based on what you're observing. Okay? So there's our numerator, denominator stuff. There's a bunch of examples there. This one, if you're okay with some mathematical manipulations, you're okay to look at this. What is the meaning of the positive and the negative? Okay, we could say the size of our number. That worked out well. Okay, there's a possibility for using a negative being below 0 and a positive above 0. 10 to the minus 2 is a negative number? No. It's 0.01. That's not below 0. That's still above 0. Okay. So it is less than 1. So we could say greater than 1, less than 1. That could help out. I would argue what those signs mean is run that calculation in that location or in a different location. What do I mean? 10 to the positive 2 means do 10 to the 2 in the same location where 10 to the 2 is written. Where's 10 to the 2 written? Okay. We have fractions, everybody's favorite thing, fractions. In a fraction we have a numerator and a denominator. Where's 10 to the 2 written? Okay. Nobody sees the numerator or denominator, right? There is a denominator. What is in the denominator right now? 1. Where's 10 to the 2 written? In the numerator. So I'm going to run the calculation of 10 to the second in the numerator. I'm going to leave it where it is. 10 to the second equals 100. Okay. 10 to the minus 2. That calculation is run in the numerator, right? But I have a minus. What does that minus mean? Do the calculation, but do it in the other location. It's currently in the numerator. Where should I run the calculation? In the denominator. And this becomes 1 over 10 to the second. I lost the minus sign. That's right, because I've now interpreted what the minus sign means. The minus sign means do it in the other location. There is no way 10 to the negative 2 equals 1 over 10 to the second. Yep, actually it's true. Feel free to verify it in a calculator. It's perfectly valid. Okay. You don't like that because you're manipulating fractions? That's fine. Don't worry about it. This is one of the beautiful things of calculators. Meaning for your next test, use and bring a calculator. Right? It will help you. Okay? That means using it now, not waiting to the test to get used to using it. Okay? So don't stress about that. I'm just going to skip on here. Let's go with our converting units and our process. We already kind of touched on this, so let's give you a little bit of a harder question. That's a lie. I thought there was a harder question there. I must have deleted it. Okay. The textbook goes through and establishes the process for converting units. Okay. So we have 3 steps, a minimum of 3 steps that could scaffold up to thousands of steps. Step 1, you will always write down what you want for an answer. Okay. That needs to be your units. Right, when you go to get a job, you go into that job knowing how much roughly they're going to pay you. Unless you've never had a job, in which case you're going, I don't care, they're paying me. Right? But you come in with a number. Because if you walk in, you're like, actually, I don't, as long as they're paying me, and they say, here's your salary, it's 1 cent per day. You're going to be like, I think I can find more money by just walking around the street. Right? I'm not going to take that job. So you go in with a number in your head. Right? And if they tell you anything with the units of cents, you're probably like, I think I'll just find something on the street. Right? But if they come in with dollars, you're now like, okay. If they come in with tens of dollars, you're like, that's a lot better. Thank you very much. Hundreds of dollars, you're like, absolutely, give me the job. Okay? Then they tell you what the job is, and you go, oh, maybe not. Okay, but you have a unit in mind. So when you go through to solve your chemistry, make sure you specify what that unit is. Write that down. Okay? Step 2, write down what you're given. Okay? Step 2 can actually get tricky on you because you can be given a bunch of different things. You have to decide which thing you want to start with that is most appropriate to solving this. Step 3 becomes the next tricky aspect. You have to start leveling in different conversion factors, different one values that allow you to get from the unit that you're given to the unit in your answer. Okay? So when we deal with our metric, I can't believe I didn't have that conversion. That's one of my favorite ones. Okay? When we deal with our metric system, we've got these units. Okay? This looks like it's cycled. So let's go through and take a look at a conversion. Okay? I want to convert mass in grams to 325 milligram aspirin tablet. Okay? How could I go through and do this? Okay? So one option we did with the powers of 10. We could work with that. But what I want you to start focusing now to is not looking so much at the powers of 10, but working on the process of dimensional analysis. You have now 3 ways to potentially solve this question. You're good with your brain. Okay? Guarantee you won't be when you get to the exam, so stop using your brain outright. Okay? Or 2, deal with your powers of 10. Or 3, do dimensional analysis. So 3 different ways. What answer should you get in all 3 ways? Really? You're like, I have no idea what answer I should get. I'm not asking for the exact number. You should get the same answer all 3 ways. Okay? The reason why we're starting with conversions like this is not because we think you're stupid. We don't at all. But what we do want you to do is get used to dimensional analysis. You're used to dealing with numeric numbers and units in this system. You can deal with those powers of 10. You've learned tricks of the trade to sneak your way through it. Okay? Because you understand the unit system. You will not understand the unit system for this entire semester. Okay? Which means as soon as we remove that unit system trip or trap that you guys have been using, you now can't solve any question, and that becomes problematic. So use whatever system you want, and then use dimensional analysis. Make sense? So let's take a look at dimensional analysis. Step 1, what do I want? Grams. Okay. Officially, that's just the measurement. What's the substance? Grams of my tablet. I could have go through and write aspirin in there. Okay. Most people don't want to write all that. I don't blame you. What are we given? 325 milligrams of that same aspirin tablet. Well, look at that. I even used an abbreviation because I didn't want to write it all out. Right? In the process of setting this up, I now need a conversion factor. Right? This now becomes the trick. That conversion factor needs to do what? It needs to get rid of milligrams. So we're looking at two things, where I'm starting and where I'm ending. So look at where I start, milligrams. Is milligrams in my answer? No. So what has to happen to the unit of milligrams? How do I get rid of it? By placing it, so we heard a divide by, that's okay, place it in the denominator. That's still division. Right? If I ran just the calculation as is, I would have no units in my answer, right? The milligrams units would now cancel. Do I want no units in my answer? No, I want a unit. What unit do I want? Okay. I've now written down units. And for those of you who, well, I already wrote down the numbers. I don't care about the numbers because what you've done is manipulated in your head and done those extra thoughts. As soon as I remove your understanding of the unit, you're screwed. Write the unit down first. Now the question. Do I know a conversion factor between milligrams and grams? Okay. We just talked about it, but you should. Milli meant what? 10 to the minus 3. My power of 10 and a conversion factor will always go with the core unit. Where does my 10 to the minus 3 belong in this expression? Okay. So I'm going to call out denominator as wrong. Numerator, I'm going to say is wrong. What? That's both answers. Nope, that's not. Right? Because what you've specified is locations. I don't want the location. I want to know what that number belongs with. 10 to the minus 3 belongs with what? The core unit. What is the core unit? Grams. Remember how I said we're going to talk about core unit? This is where it shows up. Where does the 10 to the minus 3 belong? With grams. Where does grams happen to be in this particular question? In the numerator. If you go through and say, well, it belongs in the numerator, right, well, then what happens? You start placing 10 to the minus 3 in the numerator. When? Always. No, it doesn't go always. It goes with the core unit. What belongs in next to milligram? 1. Because if it is anything other than 1, what happens to the value of 10 to the minus 3? It changes. It's not allowed to change because that is the meaning of milli. Right? What would happen with your unit system now? Milligrams cancels, and you'd be left with what? Grams of aspirin tablet. What do we want for our answer? What does that mean? Almost done. Because typically on a multiple choice test, it doesn't show you work. It shows you the final answer. So what would we have to do? Punch it into the calculator. Everything in the numerator should be multiplied by each other. Everything in the denominator should be multiplied by each other. What should you do with the numerator and denominator? Divide those two. So in this case, it's really simple. All I have to do is take 325 times 10 to the minus 3, and I would get my final answer of, because everybody seems to want these, 0.325. Yes?
So that trick with moving the decimals won't ever be useful in the future?
So the issue that I have with moving the decimals, you had to memorize how to move the decimals. Right? What happens if you misremember and you start shifting the decimal the wrong direction?
Miscalculation.
Right? And for those who are saying, well, that's not a big deal, it's a multiple choice test, I'll just pick whichever answer is the closest. I know that that's what you're doing. You will have every permutation of possible wrong answers also listed as multiple choice, not just random nonsense numbers. Right? You need to know what you're doing to get the answer right.
So if we do know King Henry,
If you do, and so this is one of the other things. If I have a trick and it works every single time, how is my instructor ever going to know? You are fair game to use it as much as you want. So if you have some other trick that helps you get through it, by all means, go ahead and do so. The issue that I have with the King-Henry method is how does that work to convert between grams and moles? Well, I don't even know what moles are. Fair enough. You don't have to. Okay? The issue is that here we're developing a system that you need to follow. This is the process that works when? Every single time. When does King-Henry work? Only when shifting a decimal point. Okay? Which method guarantees you a correct answer all the time? Okay? So when we're talking about methods in this class, the ones that I show you are the ones that I know consistently work, not the ones that only work some of the time. Okay? Which sets us up with the next question. What is the mass in micrograms of a 325 milligram aspirin tablet? So we'll work through some of this. What do we know we want for an answer? Micrograms. I don't want to write out micrograms. I wish I knew the symbol for that. That was one I'm not required to have memorized, right? Okay. So this is where somebody could go through and tell you what that was. You could look at the front of the exam. Okay. It is our weird M. You could also raise your hand and say, Mike, you said I didn't have to memorize it. I'd be like, fair enough. Did you look at the front of the exam? And you'd be like, yeah, it's not there. Whoop, sorry. Let me tell you what it is. Okay. So micro is our weird M. G. What am I given to start with? 325 milligrams. Exact same process, nothing changes. I now multiply, okay, or multiply my conversion factor in here. I want the milligram unit in the denominator. What unit do I want on top? Microgram. And this is where I would say, well, did I memorize a conversion factor for that? No, I didn't. But when I flip to the front of the exam, I am told that mu is micro, and micro equals 10 to the minus 6. 10 to the minus 6 what? What does micro apply to? Grams. Is microgram grams? Is milligrams grams? No. What does that mean about this conversion factor? It's useless. I don't know that conversion factor. Okay? That doesn't mean I give up. What that means is I'm going to have to try and convert to something else. Okay? I'm going to decide that I want to try and get rid of the milligram unit. Okay? What could I convert that milligram unit to? How about grams? Okay. I'm not even concerned necessarily about what the numbers are, but it's a good question to ask. Am I responsible for knowing the relationship between grams and milligrams? Yes. Okay. As long as it's yes, we can move on. Is grams the same thing as micrograms? No. So what needs to happen? I need to convert it. In that conversion factor, what needs to happen? What do I want to get rid of? Grams. What unit do I want? Micrograms. Do I have that conversion factor? Yep, that was given to me at the beginning. Now that I know that I have those conversion factors, I can go back through and plug in numbers. What is the relationship between grams and milligrams? What does milli mean? 10 to the negative 3. Where does the power of 10 go? Numerator, I will say, is wrong. Where does the power of 10 go? The bottom, I will say, is wrong. Where does our power of 10 go? It always goes with the core unit, period. What is the core unit in this conversion between milligrams and grams? Grams. It is the unit that shows up in both locations. Okay? So the power of 10, 10 to the negative 3 grams, is 1 milligram. Okay? The next one, grams and micrograms. Do I know what micro means? 10 to the negative 6. Okay? Where does the unit of 10 to the negative 6 go?
Grams.
Goes with the core unit, which in this case is?
Grams.
Now what happens? Now I've got a calculator, and I go through and enter it into the calculator and get my answer. Okay? 10 to the minus 3 is a multiplication. 10 to the minus 6 is a division. Your answer comes out to be 325,000 micrograms. Okay? I think I did that one right. Yeah. Kind of makes sense? How many of you look at this and be like, that's some easy calculations, I don't need to write any of this down? Does anybody feel like you don't need to write it down? And that's okay. I'm going to call BS. There's at least 5 or 6 of you that I can see are looking at this being like, this is dumb, I don't need to write this down. Okay? This is what you need to do as a process. Okay? Not because you need it for solving this. You need it for solving stuff later in the semester. That is the only reason we're talking about it. We're giving you an opportunity now to test your method versus my method. Not to see that either of us is wrong, because both of us will be right. Okay? But the opportunity here is to see that my method does work. That's all I want you to get out of this. As long as you trust my method, when we move into the next section and your method doesn't work, you now have something else to use. That is the only reason. Okay? Ignore that. So, powers of 10, those are easy to shift. Do this one. No powers of 10. Okay? The length of an American football field, including the end zones, is 120 yards. What is the length in centimeters? This is one of my favorite conversions. Okay? You've got a bunch of conversion factors listed down at the bottom. You've got some up the top. Set it up. If you get stuck, raise your hand. Talk to me. I'll come to you. Answer.
Centimeters.
We want centimeters. What are we given?
120 yards.
120 yards, which I will abbreviate YRD. Okay. Ideally, what would happen? Place yards in the denominator so that the yard units cancel, right? What do I place in the numerator? Ideally. In the ideal perfect world, how many steps do you want to take to do this calculation? 1, right? We would want centimeters. Is that a valid conversion? We don't have that. Yes, you can use the internet, Google all you want. You won't have that on the test. You can't use Google. Okay? So you've got to use the information at hand. We don't have a valid conversion factor for that, which means you now get to choose, what do you turn yards into? That is a rhetorical question. That's why I like this question. Not because I like telling everybody they're wrong, but just calling attention to some issues. I won't answer that question yet. If we go through and take a look at this question, we need to go through and deal with our conversions. Okay, so I've got 2 outlined formats up there. I believe I have them outlined correctly. Okay, so those people that did it with 2 steps, I think went from yards to meters. Okay. Where did you get that conversion from? 1 yard equals 0.914 meters. Okay, I agree. That seems reasonable. So we'd say 0.914 meters, 1 yard. You then said meters to centimeters. Where'd you get that one from? Because that's not listed. You have to have it memorized. You know centi means 10 to the minus 2. Your power of 10 goes with the core unit, being meters. We could enter this into the calculator because a couple people did do this. What did your calculator spit out? 10, 9, 6, 8. You don't have to give me any more numbers, so we'll just leave it at that. Bottom one, 120 yards. You probably didn't go to meters. You might have gone to feet. Why would you have picked feet first? Well, it was probably the very first conversion factor there. That might be a solid reason why you did that. That's okay. What's the conversion factor between yards and feet? Well, 3 feet is 1 yard. Okay. You then said feet. It's not the right answer, and ideally we'd go to centimeters, but I can't do that. But I do know feet to inches. And interestingly enough, Mike is such a jerk, he didn't even trust you to know that. Yeah, it's harsh, isn't it? I apologize. And then we said inches into centimeters. Where do we get that one? That was this up at the top. 1 inch is 2.54 centimeters. When we enter this into the calculator, we get 10, 9, 7, 2. Anybody see a problem with this? Depending on how you solve, you got different answers. Why is that the case? Okay. And it's not just a significant figure issue per se. Where this is coming into play is that we're looking at converting between systems, English and metric. The English to metric conversions are not clean conversions. Okay? Which means things spiral out of control very quickly because there are multiple ways to go through and do those conversions, and you end up seeing a drift in your answer. This is a big reason why we don't crosstalk between, say, the English system or American system and the rest of the world. Okay? Because we have to entirely retool to allow for that crosstalk to come out accurate. Because if we don't take into consideration appropriately, we see this drift, and that drift can result in the complete failure of that device. Okay? So between systems is awful. This is why we should have one universal system. This is why science tends to stick in the metric system and not drift outside it. Right? Because we're trying to communicate globally, not locally. Okay? Which brings in the next question. I still said both of these answers were wrong. Okay? And as someone then started to suggest or think back to, said the calculations are fine, the work is fine. I'm positive I entered that into the calculator right, and I will agree with you. Anybody that got either of those two answers did enter it into the calculator correctly. However, you are still wrong because you didn't take into consideration the thing at the very beginning of this unit, which was significant figures. Meaning we have to go back through each of those calculations and decide how should we track our sig figs through. So starting with the first one up top, how many sig figs in that purple box? It's a fun little test question. 1, right? 1 or 10, only the 1 is significant. Wrong. But there's only one number. I know. That doesn't make it any more right. It's still wrong. How many sig figs in that box? 2. Better, but still wrong. Do I hear 3? Better, but still wrong. 6. Better, but still wrong. Still better, but also still wrong. It's infinite. That is a definition. Okay? There are exactly 10 to the minus 2 meters in 1 centimeter. Because it is a definition, that has infinite sig figs. How about the next one? 0.914 meters to 1 yard. Depending on how precise we get within that conversion, that 0.914 will change. Okay? That is not a definition. That is the best approximation that we can get when using how many sig figs? 3. So we've defined 1 yard. There's our infinite, and now we're saying there's roughly 0.914 meters within that 1 yard. Okay? So if I want more sig figs, I could scale in more. Okay? And yes, that is insanely more frustrating right, than the other option. Okay? Than the one that was infinite. At least we could say that doesn't have an effect. Here, that number could have an effect. And we go all the way back to the beginning. 120 yards has 2 sig figs, which means my answer needs to get reported to 2 sig figs. I go through and take a look at my number, 10968. I can only report out to 2 sig figs, which means I can report the thousands place, the 10,000s place, and the thousands place. 9 being the first insignificant digit is 5 or larger, which means I can add 1 to the previous place, and my number becomes 11,000 centimeters. No decimal point. Okay. Or, if you wanted to go scientific notation on it, was it 4? 1, 2, 3, 4. Yes. What happens with the bottom calculation? 2.54 centimeters to 1 inch. That's between systems. So we might say 3 sig figs. Unfortunately, this is such a common conversion that it has been defined to be 2.54 centimeters. Really, with all the nasty fractions? Yeah. Yes. This is where conversions can become nasty. That one is defined, which means 2.54 centimeters to 1 inch is infinite. 12 inches to 1 feet, infinite. 3 feet to 1 yard, infinite. 120 yards, 2 sig figs. My answer will come out to be 11,000 centimeters. Doesn't matter which way I calculate it, I get the exact same answer. Okay? Does this already make people a little nervous? You're like, if I take one misstep, and it's even a valid step, I can get a wrong multiple choice answer. And those numbers aren't that significantly different, right? Okay. Except, who in this classroom was already aware of this issue? Yeah, I was aware of it. Who in this classroom thinks it's a bit annoying that we would ever have to be concerned about this? That would also be me. Okay. Who would never phrase a question explicitly like this? Me. Okay. Unless maybe I'm like, did you show up to lecture where we talked about this exact question? That might be a valid time for me to ask that question. Make sense? Okay. With that, we'll just advance it a little bit. Here's the footnote. 1 inch is exactly 2.54 centimeters. Why? Because somebody sat down and said, I'm tired of doing all these stupid conversions and losing sig figs. I'm going to define it to be that. That is the end of the story. Okay. Why is 12 inches 1 foot? The exact same reason. Somebody sat down and said, that's what it is. All conversions are that system. Okay. With that, we have to go ahead and stop.